So now we're going to just briefly take a look at the relationship between the symbolic method and formal languages from computer science. And probably for people that have studied formal languages, these kinds of questions have occurred. So a formal language is a set of strings, and the natural question is, how many strings of length n are there in a given language? Well, then the answer is that we can use an OGF to enumerate them, and we can essentially use the symbolic method or view the symbolic method as an approach to solving this problem. It's a very systematic way to solve problems like this. Now, there's an issue when it comes to counting that has to do with ambiguity. Typically, in a formal language, we're just concerned about specifying the set. And it could be that there's more than one way to derive a particular string. And that's a key issue in understanding formal languages and building compilers and other things like that. So if there's more than one way to derive a string, we're going to count really all the ways to derive the string. And so we want to work with unambiguous languages. Now, without getting into detail of the study of ambiguity in formal languages, I'm just going to give some examples. So let's look at regular expressions. So a regular expression uses the concatenation or the or the star operation to specify a formal language. And if you're not familiar with regular expressions, go read up on them and then come back to this. The theorem, which is really the same as what we did for the symbolic method, but just with different notation, is if you've got enumerating OGFs for two REs, and you take the OR, then the OGF is the sum. If you take the concatenation, the OGF is the product. And if you take A star, it's 1 over 1 minus. And it's really the same proof as the symbolic method with different notation, as long as the REs are unambiguous. So one thing that this says is that the OGF for an unambiguous RE is rational. Because all you get out of here is a ratio of two polynomials. No matter how you apply these operations, you're going to get the ratio of two polynomials for the OGF. Just to kind of highlight the point, another way to say this is that OGFs that enumerate regular languages are rational. So that is a language, regular language is, there exists an RE, doesn't necessarily have to be unambiguous, but there's a construction, a well-known construction that gives an unambiguous regular expression for any regular language. One way to define a regular language is that there exists a finite state automaton for the language. And then Kleene theorem is, if you look at the details of Kleine's theorem, it takes a finite state machine and gives a regular expression that is unambiguous. And then if there's an unambiguous RE, then it's rational. That's just a quick look at the landscape with regular expressions. And it's a kind of fun way to think about enumeration problems, because people maybe are more used to regular expressions. But there is the issue of ambiguity. So like we did binary strings with no zeros, this is that derivation in regular expression language. So that's an RE for binary strings with no 0, 0, 0. An unambiguous one, and then just applying the theorem, it's going to be for the star it's 1 over 1 minus, and for the tail part it's just that. It's pretty much the same ratio of two polynomials that we had in the case when we did it using the symbolic method. We get the same result, of course. And again, expanded in the same way. Here's another example. What about binary strings that represent multiples of 3? This is a famous example of, say, a finite state machine with 3 states, you can derive a finite state machine for this, or you can get this regular expression. And again, that's about regular expressions to believe that this is multiples of 3, but that's the one. This is 3, 6, 9, 12, 15, and so forth. So how many binary strings represent multiples of 3? Well, we can just apply the theorem to that regular expression, and we get this rational function that after a while we can simplify down to that simple ratio of two polynomials. And this one actually expands explicitly with partial fractions. It's going to be asymptotic to 2 to the n minus 1 over 3. And that's what you'd expect. You always have a 1 bit, and then you get 2 to the n minus 1 possibilities, and a third of them are going to be multiples of 3, approximately. There's a minus 1 to the n to make it come out exactly. But this is a fine example of enumerating regular languages. So it's just the symbolic method in different notation. Similarly, for context-free languages, where we have non-terminals and we use or concatenation, again, the same idea works as for the symbolic method. The key is to make sure that it's unambiguous. Now, it's a more complicated situation because we have multiple equations, and there's a discussion in the text about the idea that OGFs that enumerate context-free grammars are algebraic. So an algebraic function is a function that satisfies a polynomial equation's coefficients or polynomials with rational coefficients. And again, that's just a natural follow-on from just the basic rules that we're using to develop these generating functions. Now, actually the constructions that we've considered are all unambiguous context-free grammars, just using different notation. So that's binary trees, but this is binary trees as a context-free grammar. And so then the OGF is going to satisfy, it's an algebraic function because it's a solution to an equation like that. It can be recursive. So this is for bit strings, and it's a little more complicated to represent it as a CFG, but not that big a story. Really, it's just different notation, and bit strings with no 0, 0, and so forth. Now, because of ambiguity, not all context-free grammars correspond to combinatorial classes that we can enumerate in this way, and not all constructions that we consider in the symbolic method are context-free grammars, because there's other operations that we use besides just concatenation and or. There's many other operations that we use that make the combinatorial classes that we're talking about different from context-free grammars typically. But still, there's lots of cases where it's the same thing. In those cases, it's worthwhile to be aware of that. So this is just an example for the study of random walks. So a walk is a sequence of plus and minus characters, and there's lots of applications of random walks, so-called gambler's ruin problems, and also the study of some sorting algorithms. These are discussed in the text. Just from the idea of a sequence of plus and minus characters, there's all kinds of natural questions that arise, like how many different walks of length n are there? Or how many different walks of length n are there where every pretext has more pluses than minuses? That is, it stays above the line because you're going plus more than you go minus always. And similar questions like that are studied in all different types of applications. It's a relatively general framework. And so the key to studying random walks in this context is to come up with an unambiguous way to decompose them. So that's a typical walk. And here's one way to come up with an unambiguous decomposition. First one is to consider the class U, where the walk always stays above the line. Always got more pluses than minuses. So you can make a U by either just taking a plus, or by having a U and then appending another U to it, and then having a minus. So it starts at the baseline with a plus, and it ends at +1, never hits 0. That's a U. And that's an unambiguous way to define a U. And similarly, you can have a D that starts with minus, ends at -1, never hits 0. And you get a D by putting two Ds together. And then what those are good for is that they give a way to define a random walk that begins at 0 and ends at 0. So either it's a U that takes another minus to get at 0, and then you have one that begins at 0 and ends at 0, or the first step is down and you have a D, and then you go up and then have another S. So this is a context-free grammar, just using these three constructions. That's an unambiguous decomposition of a random walk that starts at the origin and ends at the origin. And that construction then, that's a context-free language, then we can use the symbolic method to get generating functions equations. This time it's 3 equations in these 3 unknowns. In solving those equations simultaneously, they're like the tree equation actually, and the end result is that the number of such walks is 2n choose n. There's lots of easier ways to prove this result, but the approach generalizes to cover many similar, more difficult problems you can read about in the text. So that's context-free languages, counting in context-free languages using the symbolic method. Next, we'll look at tries.